From this lecture, we will enter the longitudinal stability derivatives. And in this class, we will study three stability derivatives. They are Cxu, Cx alpha, Czq, and they are all about the change in forces. The first parameter we are going to derive is Cxu, x force change due to longitudinal velocity. Okay, we are having this aircraft again, but now it's in a side view. And since we are looking at the x force, and we need to analyze the force acting on the aircraft first. So what we have is thrust from the engine, and we have the lift from the wing. And notice that the wing is usually has a small angle of attack during cruise condition or level flight. So the lift force acting on the wing is not perfectly vertical, but has a small angle of attack, alpha. And the last force is the drag on the aircraft. Okay, so then in total, the force x force can be calculated T minus L sine alpha minus D. So this is what we have. And now we're applying an assumption, because usually we assume that alpha, or the angle of attack of the wing during cruise condition, is small, so L times sine alpha is becoming negligible. So the x force can be approximated by T minus the thrust minus the drag. Okay, then we just do the derivative partial x partial u. So this line repeats the assumption we are applying. Okay, so now we do the derivative partial x partial u, and so each component need to do the same operation. So partial t minus partial u minus partial d partial u. And okay, so we can assume in level flight, the change in horizontal velocity is a change in total velocity. Okay, and then we have xu equals partial t partial v minus partial d partial v. So we are replacing the small u by v. And okay, and because we know the drag is cd times half rho v squared times s, and then we just plug it in. And now we need to apply another assumption, which is the thrust is hardly changed by your true airspeed. So partial t partial v is approximated by 0. And now xu becomes minus cd rho vs. So we did the derivative with respect to v. Okay, and the last step is for the non-dimensionalization, we need to find a denominator for this xu parameter. Okay, so the denominator is half rho vs. So eventually we have this relation, cxu equals minus 2 times cd. So it becomes more straightforward, right? More concise. So the change, x force change due to longitudinal velocity is minus twice the drag coefficient of the wing. So this is what we have for Cxu. The second derivative we are looking at is Cx alpha, the x force change due to angle of attack. And we already analyzed the forces, three forces acting on this aircraft. We have thrust, lift, and drag. And also we know x equals t minus L sine alpha minus d. And now what we're applying is a small angle of attack assumption. And in cruise condition, alpha is a small angle. And then we can simplify x equals t minus L alpha minus d. And since we are looking at the parameter x alpha, partial x partial alpha, so we need to find a relation between x and alpha. Seems now we get the relation x, the right hand side, do you have an alpha? Okay, and so now we are making the x non-dimensional, the force coefficient. So Cx equals x divided by the half rho v squared times s, which is the denominator we use for the force. Then we have on the right hand side Ct, the thrust coefficient, minus the lift coefficient times angle of attack minus the drag coefficient. So we have this combination, and we will do the derivative now. So we have Cx alpha, which essentially is partial Cx partial alpha, because alpha is calculated with dimension of 1 in radian. So and the denominator is essentially the same. Okay, and on the right hand side we have Ct alpha minus Cl, because alpha is divided, eliminated, and minus partial Cd partial alpha. Okay, and usually the angle of attack won't give a lot of change in thrust. So Ct alpha, we can assume it being 0. And then we can simplify this Cx alpha. It equals minus Cl minus partial Cd partial alpha. So this is what we have. And it's still not the final answer. We can actually walk further, because in practice, the drag coefficient can be estimated by the Cd equals KCl squared divided by pi times the aspect ratio. AR is the aspect ratio. And you may wonder why we get this type of relation. It's probably it's data regression from some wind tunnel measurement. So link Cd with alpha, and the K is a constant. Okay, and then partial Cd partial alpha becomes K divided by pi AR times the derivative, and so we just do the derivation. I'm not reading it. So eventually we have partial Cl partial alpha times something, and we know partial Cl partial alpha is the slope of the wing lift coefficient, right? So we can replace it by A, the slope of the lift curve coefficient. So that's the partial Cd partial alpha. Okay, and then we just plug in. This is what we derive eventually. Cx alpha equals minus Cl minus 2k alpha Cl divided by pi times the aspect ratio. So this parameter Cx alpha, x force change due to the angle of attack change, is mainly related with the lift coefficient and the aspect ratio. The last derivative we are looking at is Czq, the z force change due to pitch rate. And the z force is actually the force in the vertical direction. Okay, and we have this aircraft without any surprise. And now what happens is there is a positive pitch rate acting on the aircraft. So since it's positive, if we take our right hand, and so the pitching is kind of counterclockwise. So the vector is acting pointing towards into the screen. Okay, and so first of all, the aircraft is in a positive pitch rate Q, and what happens on the elevator plane is there will be a downward vector, and so you may wonder how to get this vector, velocity vector, and so we need to know the moment, the arm, the distance between the aerodynamic center of the elevator and the CG of the aircraft. So we denote it by LT. So the velocity, vertical velocity is downward velocity acting on the elevator is Q times LT. That's a downward speed of the elevator. Okay. And since we know the aircraft is traveling at a speed of v, and it's the same for the elevator, so in total, there's a total velocity pointing towards left downward, and there is a small angle of attack induced, which is denoted by alpha in here. So we have the induced angle of attack. Then what happens? And there will be the induced lift and hence drag, right? Okay, so then we will have lift and drag produced on the elevator. So since we are looking at the Z force, vertical force, we need to see the component of these two forces, lift and drag, from the elevator. Okay, and again, we can estimate alpha by Q times LT divided by V, and we're already familiar with this small angle of attack assumption. Okay, I'm not repeating that procedure. So then in total, the Z force is minus, remember, the positive Z is always pointing towards ground. So that the lift and the drag on the elevator is components, the vertical component of lift and drag is negative in sign. Okay, so then we have CLT times cosine alpha plus CDT times sine alpha. That's their projection to the vertical axis, and then times half rho v squared times st. St is the area of the elevator. So we have the Z force from the elevator. That's a force change on the aircraft. And we need to do some simplification. And again, it is a small angle of attack assumption. Because alpha is a small angle, cosine alpha is 1 and sine alpha is alpha. Okay, so this is a simplification. Then we do the derivative. So dz can be denoted by partial z partial alpha times d alpha, right? So this is without any approximation. This is just a quite mathematical procedure. And then we just do the partial z partial alpha. And so the alpha besides CDT can be eliminated. And in a bracket, we have partial CLT partial alpha plus CDT. And then times half rho v squared times ST because it's a constant. And then d alpha. So we can plug in alpha. So d alpha equals d bracket Q times LT divided by V. So we have this the expression of dz. Since we are looking at dz, dq, partial z, partial q, and on the right hand side we do have q, dq in a bracket, right? Okay, so we need to do some simplification further, and this is what happens. I'm not reading it. And okay, so the next step is we calculate partial z, partial q, and we have. So we just do the derivative of dz, and then we have the dq is eliminated on the right hand side. So eventually becomes this expression. And now we know partial CLT partial alpha is actually the elevator lift coefficient slope. It's a constant. So we can replace that partial derivative with AT, a constant. Right? So now we have ZQ, and it's actually contributed by two components. One is the lift from the elevator, the other is a drag from the elevator. We move further, and so I'm pasting the relation ZQ, and the next step to find the non-dimensional derivative CZQ is we need to find the denominator. In this case now is half rho v SC. And when you look at the table to find a denominator, you need to remember now we are looking at the longitudinal coefficients. So we need to go to the longitudinal part instead of the lateral directional part we worked on in all the previous lectures. Okay, so that now it's half rho v SC. So why is C? Because in the longitudinal domain, and the characteristic length is usually the mean aerodynamic chord. Okay, so we do some simplification. Then we have on the right hand side is minus STLT divided by SC bar, and then bracket times the bracket AT plus CDT. And similarly, we can define STLT divided by SC is the tail volume. And because it has STLT has a dimension of volume, and the tail volume is actually a ratio between the elevator volume and the wing volume. Okay, then CZQ can be approximated by minus VT, that's a tail volume, times AT plus CDT. Okay, usually we know the constant AT, that's the slope of the elevator lift coefficient slope, is far larger than the drag coefficient. So we have CZQ can be approximated by minus VT times AT. So it's more simplified, and we can usually use it as the first estimation. So this is what we have for this lecture. We derived the 3 parameters, and hope you can understand.